So this next example asks us if the given set of vectors are linearly independent and whether they form a basis for R cubed. Well, to check if something forms a basis for R cubed, there's actually two things that we're going to have to check. We need to determine if they are linearly independent. So something we have to do already. Independent. And whether they span R cubed. Okay, so it's actually just go ahead and take a look. The first one I have 1, 0, 0, 0, 1, 0, and 0, 0, 1. So we actually knew already that these guys are the basis for R cubed. So we kind of knew immediately that they are linearly independent. And they also have to span R cubed. But let's just say we don't know these facts beforehand. How would I go about and checking this thing? Well, to check if they are linearly independent, the definition is that I need to solve the system of this vector equation. So something times the first one plus something times the second one plus something times the third one. And I want to set my right hand side to be just the zero vectors. If they indeed are linearly independent, then the only solution to this vector equation is better be all zero, just the 0, 0, 0. So let's write the augmented matrix for this system. I'm gonna have here 1, 0, 0, 0, 1, 0, 0, 0, 1, and then my right hand side is just all 0. And lucky for us, this matrix is actually already in the reduced row echelon form, so I knew the only solution that we have is going to be that x equal to 0, y equal to 0, and z equal to 0, so they are indeed linearly independent. Now, how about do they span R cubed? Well, what is R cubed? Well, R cubed is basically just a vector, just a set of vectors where there are three coordinates and all of the coordinates are real numbers. So these three numbers, they can be anything. Now then, to check if these three vectors span R cubed, so I need to check that this guy ABC, whatever ABC is, this has to be a linear combination of my three vectors here. In other words, there needs to be a solution to this vector equation. C 0, 0, 1. Okay, and once again, I write the augmented matrix for this vector equation. Wait a minute. Okay, this needs to be 0, 1. And once again, this is already in the reduced low echelon form. And the solution is x just equal to a, y equal to b, and z equal to c. And that actually kind of makes sense because if x equal to a, and y equal to b, and z equal to c, then my left hand side and my right hand side are equal. Notice also that the solution here is actually unique. And this is one of the property of a basis that we talked about earlier. Whenever, for any vector in my space, it can be written uniquely as a linear combination of its basis. Okay, so let's move on to the next one. What is this? What the? So I need to check if these three guys are linearly independent. I'm just gonna go ahead and shorthand just in depth, and I need to check if they span R cubed. Okay, so let's go ahead and start with linearly independent. So I'm gonna need to solve this vector equation. So x times the first guy plus y times the second guy plus c times the third guy. And my right hand side is going to be all 0. Well, the augmented matrix, I'm just going to collect the coefficient. 3, 3, 0, and then 3, 3, 3, and then 0, 0, 0. Now then, let me just go ahead and row reduce this guy. The row echelon form for this augmented matrix is going to be 1, 1, 1 in the diagonal, 0 everywhere else, and my right hand side is going to be all 0. So once again, I have that the only solution to this system is 0, 0, 0. So once again, these three guys, they are linearly independent. Now then, do they span R cube? In other words, can I write any vectors in R cube as a linear combination of these three vectors? Now it's actually just going to be the same left hand side. So I'm just going to kind of copy that down here. Whatever. Now then, you can go ahead and write the augmented matrix and do the row reduce, but let me actually just conclude that indeed that's going to be a solution, and so this guy span R cube. So they basically form a basis for R cube. Another thing that I would like to mention as well is that because R cube, this guy has dimension 3. And this guy, we actually have 3 vectors here. So one thing that is going to happen is that if I have 3 vectors in a vector space, if I have 3 vectors in a vector space that has dimension 3, if they are linearly independent, they will automatically span that vector space. In other words, if I have a vector space of whatever dimension and I have that many vectors coming up, if they will be linearly independent if and only if they span that vector space. So if number 3 here and we have the number of vectors here are equal, then one thing will happen if and only if the other things kind of happen. So this will be helpful. For part C, I have 2 vectors, just 1, 0, 0, 1, 0, 0, and 2, 2, 0. So let me first check if they are linearly independent. So I'm just gonna go ahead and write the augmented matrix form for this one. It's gonna be 1, 0, 0, 2, 2, 0, and then all 0. And if you do the row reduce, this guy is gonna give you 1, 1. Okay, so the only solution to this system is when when all the unknown are 0. So indeed, these two guys, they are linearly independent. Now, another way you can look at this is that notice how this is actually just the same vector that we have before, 1, 0, 0, and 2, 2, 0, but I remove the last guy. Now, if I have 3 guys and they doesn't have anything to do with each other, they are linearly independent. So we can actually conclude right away without doing any of these computations that they indeed have to be linearly independent. Now, do they span R cube? Well, you can kind of check, but let me just tell you the answer that they will not span R cube. And one way you can see that without going to solve any of the vector equation is that notice how this guy there's only 2 vectors, but R cube has dimension 3, so there cannot be a basis for R cube. Well, they are linearly independent, but they cannot be the basis for R cube, so they cannot be the span of R cube. Otherwise, they would have been the basis. So we can answer this without actually doing any computation. Okay, let's move on. For my part D, I have 1, 0, 0, 20, 20, 0, and 300, 300, 300. Now, notice how these 3 guys, they are actually just a scale of what we see before. It's actually just the same vector that we have for part B, except that I scale the second one by 10. So I get 20, 20, and I scale the third one by 100. So I get 300, 300, 300. So let me actually just go ahead and tell you the answer first. This guy is going to be a basis. It will actually have all the properties that the 3 vector had earlier. It will be linearly independent. And they will span R cube. The reason why this happened is that notice how this is actually just a scalar multiplication of what we have before. And when we have just a scalar multiplication, it doesn't affect any of these 3 properties that we have here. Notice how, well, let's just take a look at, let's say if I have R squared, and let's say this 2 guys form a basis for R squared. Now, if I scale these two vectors, then no matter how much I scale it, they will still form a basis for R squared. And it can be, I can scale it to the negative as well. So let's say if I scale this horizontal guy with a negative constant, so I'm going to get this vector. So no matter how I scale a basis of a vector space, they will still form a basis for a vector space. So there's another, so that's the way we can answer this question without doing any of the computation. Okay, so let's now take a look at this next one. So are they linearly independent? Now let me actually just go ahead and write the augmented matrix. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then all 0. Now then, if I were to row reduce this guy, that's going to give me 1, 0, 0, 0, 1, 0, and then negative 1, 2, 0. Now, what does this mean? This means the solution to this system is, well, I have my x3 being a free variable, so my x3 can be anything. And now my x1 is just going to equal to x3, and my x2 is going to be negative 2x3. So that means this guy has so many solutions, so x3 can be any real number. So there are actually many more solutions to this system than just the zero vector. So this guy, this tree guy, they are not linearly independent. And like I said earlier before, I have these three guys and they live in R cubed. So once I knew that they are not linearly independent, I knew immediately that they cannot be the span of, they cannot span R cubed and they cannot be the basis of R cubed. Okay, that's for this one. And now for my part F. Notice that the first three vectors are actually the same three vectors that we see in the earlier example. And these three guys actually already span R cubed. They already form a basis for R cubed. So, these three guys, they would actually already form R cubed. Now then, if I were to put in one more guy into this system, then obviously they cannot form a basis for R cubed. Another way you can see it is that because R cubed has dimension 3, so the basis can only have 3 vectors. So when they have more than 3 vectors, then they automatically cannot be a basis. Now then, another way you can look at it is that they are not linearly independent. Notice that these three guys actually already span R cubed, so this vector here, because it belongs to R cubed, this last vector is already a linear combination of the first three guys. You can try to solve it, but let me just say that because the fourth guy is actually just a linear combination of the first three guys, when you put it in, they will be linearly dependent of the first three guys. So when the four of them show up together, they will automatically be linearly independent. But before I finish, let me actually say that this four guy would span R cubed. And that's because the first three guy is already a basis for R cubed. So if I throw in more stuff, it would still span R cubed.